Well, you know I love my molecular scene problems. So here's again a one that's going to allow us to kind of sum up a lot of the information that we've learned about thus far and relate it to a molecular scene. So in this problem, they tell us that we have two acids. We have HX, which again is going to be our blue and green, and then we're going to have HY, which is our blue and orange. And so basically we're looking at conjugate base being green for HX, and then for HY, we're going to have blue and orange. The blue really represents the hydrogen atom that's attached onto that acid. These are two weak acids, so each of them is going to dissociate in the presence of water to give us H3O plus and the conjugate base, in this case X minus, which is just going to be a single green species, and then H3O plus and Y minus, which is going to be a single orange species. So another piece of information that they give us is that when we have 0.1 molar of each solution, we're going to have a pH of 2.88 for our HX solution, and the pH is going to be equal to 3.52 for our HY solution. And so what we need to start out realizing is, so it's asking us, looking at these different molecular scenes, which one best represents equal molar solutions. And so what we need to think about is what it means to have these different pHs. Well, what it means to have these different pHs is pH of 2.88 means that HX is a stronger acid. Okay? And if HX is a stronger acid, that means it's going to dissociate more. So we're going to make more of the green spheres compared to the green spheres that still have their hydrogen atom attached. So let's kind of start looking at these scenes. And so let's look at scene one and see if we can see what's going on here. In this scene, if we just look at the orange, we can see that for each species there's kind of 6 total green spheres and 6 total orange spheres. And for both of these, we have an equal number of orange spheres without their protons, orange spheres with their protons. So we really have a one-to-one relationship of, in this case, it's HY to Y minus, and we have a one-to-one relationship between HX and X minus. If this was the case, we would predict these would have equal pHs because they have equal acid strength. They're both contributing the same amount of H3O plus to solution. They're dissociating the same amount. So scene one is not going to be it. Let's look at scene two and do the same analysis. If we look at the HY to Y relationship, in this case, we only have a 1 to 2 relationship. We've got a lot more HY that has dissociated. And if we look at the HX, we can see that it's the opposite. It's 2 to 1. So again, we're starting to get towards what we'd want. We want a difference in the amount of dissociation for HY versus HX. But in this case, since HY dissociated more, in this case we would predict that the HY solution would have a lower pH. And that's not what we see. So this is also not the correct scenario. Finally, looking at the last scene, we can see that it's the opposite of what we see here. We see the 2 to 1 relationship of HY to Y minus and the 1 to 2 relationship of HX to X minus. Again, HX having dissociated a lot more means that that's going to be the stronger acid. So HX is a stronger acid. We'll get to a sample problem a little bit later that actually has to do with quantifying this extent of dissociation. So we'll get to that a little bit later. But again, for this case, just a qualitative problem that gets us to think about dissociation, the generation of conjugate bases, and stronger acids dissociate more, generating more of their conjugate base species.